Okay, let's start today's lecture. Last time we defined the four-dimensional motion, four-dimensional vector of velocity, a four-dimensional vector of momentum, and the four-dimensional vector for the force. So basically, we generalized the idea Newton developed in Newton's mechanics, like force and momentum, into 4D vectors. Okay, and today we will utilize what we derived in the previous lecture to write down the equation of motion and look at the consequence of the equation of motion. Okay, so first let's look at Newton's mechanics. In Newton's mechanics, we know the Newton's second law, which is the most probably one of the most important law from Newton, which gives us the equation of motion. Looks like this. On the left-hand side, we have force, which is the cause of the motion. On the right-hand side, we have a quantity that describes the motion, which is p, the momentum. Okay, so Newton told us force should be the time derivative of momentum. Okay, now we know we are in the 4D space in special relativity. In special relativity, we should write every equation in terms of scalar equals scalar, a 4D vector equals 4D vector, etc. Okay, so we need to generalize this formula to be compatible with the principle we discussed in the previous lectures. That's the only way to guarantee that no matter what reference frame we are using, we get exactly the same physics, exactly the same physics law. Okay, so how do we generalize and how do we modify Newton's second law? Okay, first of all, for the force, we know that we cannot use the old three-dimensional force anymore. We need to use a four-dimensional vector of force. And as we showed in the previous lecture, the four-dimensional vector we should utilize is this one. Okay, so this is a four-dimensional vector up to a factor of gamma. The last three components are the force defined by Newton. And in addition, we also have one additional component. This additional component is power. Is power done by this force divided by speed of light. Okay, so we replace force by this four-dimensional vector. That's the left-hand side. For the right-hand side, we know in Newton's law, momentum is a 3D vector. But instead of 3D vector, here we should utilize a four-dimensional momentum, which we defined also in the previous lecture. Okay, so this four-dimensional momentum, the last three components are proportional to Vx, Vy, Vz, pretty much similar to the momentum we learned in Newton's mechanics. However, the coefficient is not a simple mass. The coefficient is the rest mass of the object multiplied by the gamma factor. Okay, and the first component of this momentum, 4D momentum vector, is speed of light. So gamma times m0 times speed of light, that's the first component. The rest three components are very similar to the momentum Newton told us. Okay, so we have force, which become a 4D vector. Momentum become 4D vector. We still need to do one more step. Okay, that last step is a time derivative. In Newton's law, Newton just say, let's do a time derivative. But here we know that in special relativity, we need to be very careful about what time we should be using. We can't use just a regular time or say the lab frame time. The reason is because time, the lab frame time, is not a scalar. It's actually part of a vector. Okay, we can't use part of a vector to define equation of motion. We need to use the whole thing so that we can get scalar equals scalar, vector equals vector, tensor equals tensor. Okay, so we can't do a regular time derivative. Instead, we need to do a scalar time derivative where dd tau. Okay, so instead of dt, we should use d tau, and this tau is a proper time. Okay, so this is the same trick we used early on when we define velocity. Okay, when we define velocity, we also need to do the time derivative, but we can't do that because time derivative is not a scalar, neither a vector. It's part of a vector. We can't use part of a vector. So we need to replace this time derivative with proper time derivative, dd tau. Okay, once we do dd tau, the proper time derivative, proper time and proper time derivative, this object is a scalar, and the scalar times a vector is a vector. So the right-hand side is a vector. The left-hand side is also a vector. It's four-dimensional vector. So this equation of motion satisfies the structure of vector equals vector. And this physics law will stay the same in different reference frames. That's the generalization of Newton's second law. Okay. Oh, and by the way, for the proper time, we know the proper time and the lab time are related by a gamma factor. So here, if we utilize a chain rule, same as what we did in the previous lecture, we can show that the time derivative for proper time, sorry, I think there is a typo. This one should be ddt, not dd tau. Okay, so time derivative for proper time is the time derivative of a regular time derivative times gamma. So we should replace this one. We can replace this proper time derivative by ddt, but we need to multiply a gamma factor in front. That converts proper time back to a regular time. Okay, so this will be the equation of motion where we should be utilizing the special relativity. And this is a generalization of Newton's second law in special relativity. Okay? So Newton's second law itself in special relativity is not the structure of scalar equals scalar, vector equals vector, tensor equals tensor. So Newton's second law itself, we cannot utilize that. Because that physics law, the original Newton's law, will not stay the same in different reference frames in special relativity. If you do a Lorentz boost, this quantity will change. This equation will change. It cannot stay the same. But in this 4D version of modified Newton's law, everything is a vector on one side and a vector on the other side. So no matter which reference frame we are using, this equation of motion will stay the same. Okay, so this is the equation of motion. And we can simplify this equation of motion a little bit. For example, we have gamma on one side, we have gamma on the other side. We can cancel these two gammas. Okay, if we cancel these two gamma, what we get is this equation. Okay, this equation is also vector equals to vector. It satisfies the same thing. Okay, and if we look at this equation, this 4D equation, because it's vector equals to vector, is actually 4 different equations. We have one equation for each component. Okay, let's first look at the last 3 components first. Then we will look at the first 3 components afterwards. Okay. So for the last 3 components, the second component is fx. For the other side, the second component gives us the time derivative of vx. So the second component is this guy. And third component on both sides should be equal. That gives me this equation. The last component on both sides should be equal, which gives me this equation. Okay. So the last 3 component of the left-hand side equals the last 3 component of the right-hand side gives me 3 equations. Okay. So these 3 equations are very similar to Newton's second law, but it is, as we said, it's a modified version of Newton's second law. This equation is nice because this equation, this physics law, stay the same in different reference frame if we do Lorentz boost. Okay, so let's look at this. So remember in Newton's law, we know that force is dp dt, momentum derivative of time. Okay, so if we look at these equations, then what is our momentum? This is our momentum. Okay. So we can call this guy as momentum px. This guy is my momentum py. This guy is momentum pz. Okay. If I call this px, this py, and this pz, then this equation of motion actually looks the same as what we have in Newton's mechanics, F equals to dp dt. Okay. It looks similar to Newton's mechanics, but there is a fundamental difference. That is, our momentum is now defined like this. Okay. It's defined like this. Okay, so in Newton's law, we know the momentum is mass times velocity. Here, the momentum in special relativity is gamma times mass times velocity. Okay, and this gamma factor depends on velocity. Gamma is a function of velocity, which means the ratio between momentum and the velocity is not constant anymore in special relativity. Okay, so instead, this coefficient which we use to define momentum is a function of velocity. Okay. So momentum is proportional velocity, but the coefficient is not constant. The coefficient is actually a function of velocity. And very typically, we define m0 times gamma, m0 as gamma, as m. So this m is my new mass, okay, the mass of my object. And this mass is related with the rest mass m0. M0 is the rest mass, the mass of the object when the object is not moving. I'll say if we use a reference frame, in this reference frame, this object is not moving, we can define the mass. Okay, and that's the rest mass. And the rest mass times gamma, again, gamma depends on velocity, gives us the mass of the particle. Okay, so different from Newton's mechanics. In Newton's mechanics, mass is a constant, is a physical constant of object. But in special relativity, mass depending on reference frame. In different reference frame, you have different velocity, you have different gamma, and thus you have different mass. Okay, but so nevertheless, if we define the mass this way, and we allow the mass to increase when we increase the speed of the particle, then this equation of motion, the last three components, is pretty much the same as what Newton told us. F equals to dp dt. The only thing we need to remember is this momentum p is my relativistic mass times velocity. And the relativistic mass is my rest mass times this additional gamma factor. Okay. And remember, and the gamma factor is this, 1 over the square root. This is gamma factor. So in other words, in special relativity, I can think of my object as having a mass, and that mass is my rest mass divided by square root 1 minus velocity square over c square. Okay, so this is the mass of my object, and the mass of my object depends on velocity. When the velocity gets larger and larger, my mass of my object is also getting larger and larger, and this mass diverge becomes infinite if the velocity approaches speed of light. If the velocity approaches speed of light, the denominator becomes 0, so my mass becomes infinite. So this is why Einstein told us when we increase the mass, increase the speed of particle, this particle's mass will become larger and larger and eventually diverge when the speed approaches the speed of light. Okay, so nevertheless, so in summary, Newton's law more or less survived, except that we need to keep in mind the mass is not our old physics constant anymore. The mass depends on velocity in this way. Okay, so the rest mass is still an intrinsic property of the object. Okay, it doesn't matter how much, doesn't matter which reference frame we are using, but the mass depending on the velocity in this way. Okay, so that's one of the very important conclusion Einstein told us. For a relativistic particle, its mass changes with velocity. Its mass a function of velocity. And if you use this mass to define momentum, Newton's second law still survives. Okay, so that's the last three components. So last three components recovers Newton's law with one small modification, which is the mass of my particle. Okay, and finally, before we go to the next topic, one more thing to highlight. This theory of special relativity recovers Newton's law. It recovers Newton's law if the particle's velocity is small. We know that if the velocity v is small, gamma is 1. If gamma is 1, then the mass actually becomes just a rest mass. So this is actually what Newton told us, the mass becomes a constant. Okay? So Newton's law is actually still accurate as long as the velocity of my particle or my object is much smaller than the speed of light. Okay, so that's the last three components of my four-dimensional equation of motion. Now let's look at the first component. Okay, the first component on one side is P over C. And remember, this P is power. Okay, it's not pressure. It's not momentum, it's power. And the right-hand side, left-hand side is power of the force over C. And the other side of the equation is the time derivative, gamma times rest mass times speed of light. Okay. So the first component of my four-dimensional equation of motion is this. Power equals to time derivative of gamma m0 speed of light. And let's multiply speed of light on both sides of the equation to get rid of this 1 over c for the left-hand side. Okay. If you multiply speed of light on both sides, the speed of light down here is canceled out. So I find that the first equation, the first component of the equation gives me power equals this guy. Okay. And what is power? Power by definition is a time derivative of work done by the environment to the system. Okay. Power is dW dt. W is the work done by the environment to the system. And according to the energy conservation law, if the environment do some work to my system, the energy of my system should increase. And the energy increase should be exactly the same as the work done to the system. So the time derivative of work is actually the same as time derivative of energy of my system. Okay? So dW dt is actually the same as dE dt. E is the energy of my system. So the left-hand side of my equation power, I can rewrite this as dE dt. The energy of my system take a time derivative. Okay? So that's the left-hand side. The right-hand side is also a time derivative. Okay? The time derivative of gamma m0 c square. Gamma m0 c square. Okay? If we have a time derivative of the object equals to time derivative of object, this differential equation is extremely easy to solve. Okay? This just tells me the left-hand side E and the right-hand side gamma m0 c square equal to each other, but up to some constant. Okay, so we can always add some constant here. Constant is okay because if you take time derivative, constant time derivative or time derivative of constant is 0, so the time derivative, the constant doesn't gives me anything, so these two time derivative will be equal. Okay, so the bottom line from the first component of my equations of an equation of motion, I find that my energy equals to gamma m0 c squared plus a constant. And what is gamma m0? Well, gamma m0 is what we just defined as mass. Okay? Gamma times 0, it's gamma times m0 times rest mass is a mass we define in special relativity. So gamma m0 is actually the mass, the special relativity mass. Okay, so this equation immediately tells us my energy is mass speed of light squared. So this is a famous relation E equals to mc squared. Okay, and this relation is not something fancy, not something like comes out of nowhere. It is a natural requirement as long as we want our equation of motion to take the structure of 4D vector equals to 4D vector. And as long as we want this theory to recover the law of Newton when velocity is small, then we have no other option. We have to write down the equation of motion looks like this. And the first component of my equation of motion gives me this relation. It has to be true. Okay, we have no other option. As long as we want at small velocity we recover Newton, and as long as we want to require that different reference frame have the same speed of light and the same physics laws, this is a natural consequence. There's no other option. Okay, so this is where m equals to E equals to mc squared comes from. Okay, and I do want to say a little bit more about this relation. Okay, as you may have noticed, this relation I show you here is not it's not yet m equals to E equals to mc squared. It's not yet. We have additional constants. Okay, so in other words, from this equation, we cannot yet say mass is the same as energy, energy is the same as mass. Okay, in order to say mass is the same as energy and energy is the same as mass, we need to do one more thing. That is to show energy and mass can really convert into each other. Okay, if they cannot be converted into each other, if energy is energy, mass is mass, there happens to have some relation between them, but they cannot convert them into each other, then it makes no sense to say energy is mass, mass is energy. Okay, they are only the same thing. They can only be the same thing after we find a way to convert energy to mass or convert mass to energy. Okay, and from the mathematical point of view, this is related with this unknown constant we put here. Okay, so by solving the differential equation we have here, we know that there is an arbitrary constant we can put here in our solution for this equation of motion. Okay, and what is this constant? Okay, if this constant is 0, then we have energy equals to mass up to c squared factors. If this constant is non-zero, then energy is not quite mass, but with some shift. Okay, so how do we think about this constant and what value of this constant we should take? Well, let's look at this constant. Okay, so the constant, what is a constant in energy? So first of all, the first thing I want to point out is that for energy, the constant actually doesn't matter. We can shift energy all the energy by an arbitrary amount and still describe the same physics. The reason for that is the energy of the system, what do we use energy? Okay, we don't really care the energy of the system. What we really care is the energy conversion. Okay, so say our system has the initial energy EI and the final energy EF, and this energy becomes different. E final and the EI is different. Then the energy difference between final state and initial state tells me how much work this system have done to the environment. Okay, so in physics, what we really care about is the change of energy. It's energy change, because energy change is work done by the system to the environment, and it's the impact of the system into the environment. Energy itself is not important. Okay, and to better understand this, let's think about the 0 points of energy. So what do we mean by energy being 0? Okay, and energy being 0 is actually a meaningless statement. We can set any energy to be 0. Energy 0 is just our reference point. And the reason is exactly what I mentioned here. Okay, So because we only care about the energy difference between the final and the initial state, if I shift my zero of energy, if I add a constant to my initial energy and the same constant to my final energy, the difference does not change. Okay. So in terms of energy change, I can shift the energy by a constant up or down. As long as I shift all the energy by a constant in the same way, the energy change never gets modified, and all the work done by the system would never get modified. So all the physics remains the same. Okay, so the energy, which state has energy zero, it's not really it doesn't really have a fundamental physics impact. Which state has energy zero, which state has zero energy, is more like a reference point. So we choose a reference point, say this state has energy zero, and then we measure the energy of other states in relative to this one. So this state of energy zero is a reference point. I compare another system, the energy difference between another system and this system, and the energy difference defines the energy of other system. And I can choose this state to be my zero, I can choose other state to be my zero, I can choose any state to be my zero. I just need to choose a zero reference point. Okay, this is most obvious if we think about gravity potential. Okay, so in gravity potential, we know gravity potential is mgh, but what is h? H is height, and this height is relative to a reference point. Okay, so when we define gravity potential first, we define a height. So this height will be my height zero. I call this height to be height zero. And this height can be any height. It can be here, this height. It can be the ground. It can be the sea level. And depending on whether I'm standing on, here or standing on the top of a mountain, the ground for me means different things. Okay. So for the gravity potential, we first need to define a height to be zero. That's my reference point. Then using that reference point as energy zero, I define other gravity potential. Okay. And I can choose this reference point in any height I like. Okay. If I choose a different reference point, the zero gravity potential point changes. Okay. But all the physics remains. So for gravity potential, obviously this energy zero is a choice. It's a reference point we choose. Okay. And typically for gravity potential, we choose the height zero to be the ground, to be the lowest point in this area where I do the experiment. This ground is only a convenient choice. It's not necessarily, we don't necessarily need to choose the ground level. We can choose, say, sea level, we can choose top of mountain, we can choose any height to be my reference point. Similarly, for gravity potential, if we write it as in Newton's gravity law, okay, G mass divided by the distance r, okay. For the gravity potential, again, when we write down this formula, we choose the reference point. That reference point for this formula is we choose infinite far away. When we choose when these two mass are infinite far away, we choose that to be my energy zero, to be the reference point of my energy. Okay. If I choose that to be my energy zero, then this equation is what we have. Okay. If I don't choose infinite far away as my energy zero, then I can add additional constant here. If I add additional constant here, nothing changes. All the fundamental physics laws stay the same. It's just the reference point become different. Okay. And for kinetic energy, for example, in Newton's mechanics, we know the kinetic energy is 1/2 mass velocity squared. And for kinetic energy, typically we choose velocity zero to be my energy reference point. Velocity zero is where the kinetic energy, we call kinetic energy being zero. That's a typical convention. But of course, this is not necessary convention. Okay, I can choose any state to be my reference point. For example, I can choose the state of velocity equals 1 and the mass equals 1 to be my zero energy state. Okay, I just choose this to be my zero energy state. If I choose this to be my zero energy state and the reference state, then the kinetic energy of a particle should be defined like this. I need to subtract 1/2 because that's where mass is 1, velocity is 1, I get energy 0. Okay, I can choose the reference point of energy in any arbitrary state. The bottom line, shift the energy by a constant does not mean anything. I can shift the energy by a constant and nothing changes. Okay, in that sense, this constant doesn't really matter. Okay, I can always make this constant 0 or make this constant 100 by choosing my zero energy reference point. Okay, so in that sense, this constant doesn't really matter. Okay. However, in reality, when we really do physics, this constant do matters a bit. Okay, this constant matter a bit in the sense if I choose a good energy reference point, the formula is simple. The formula is simplified. For example, for the kinetic energy, if I choose velocity 0 state to be my reference point, then kinetic energy is 1/2 mv squared. Okay, and that is very nice, and that's a convenient option. But if we choose, say, velocity equals 1, mass equals 1 to be my reference state, then my kinetic energy looks like this. Okay, and in this option, my kinetic energy sometimes is positive, sometimes is negative. Okay, so I don't know actually what the sign of my energy should be. But if I choose velocity being 0 as my reference point, then I know my kinetic energy is always positive in this conversion. And I also know if kinetic energy goes to 0, that's the lowest possible kinetic energy state I can get. Okay, so this convention, choosing velocity being 0 to be the 0 reference point for my kinetic energy, has an advantage. Advantage is twofold. First of all, I know this energy is always positive or non-zero, positive or non-negative, positive or 0. And secondly, if the energy goes to 0, I know it reaches the lowest possible energy. It cannot be lower. Okay, 0 is the lowest energy. Okay. So choosing the reference point to be the lowest possible energy is usually a good way. Okay. That is convenient. And that guarantees my energy is positive. And in the same time, it tells me if your energy is very, very close to 0, it means you are approaching the ground state, you're approaching the state with lowest possible energy. Okay. So choosing the lowest energy state as a reference point is usually a good option. Okay, so now let's go back to the m equals c squared plus constant. Okay. So what the reference frame, what the energy reference point we should choose? So which state we should call energy 0? Okay. If we follow Newton's opinion, Newton will tell us, oh, that's easy. Let's choose the state where this object is not moving as my reference point. Okay, that's what Newton did. Newton says, let's choose velocity being 0 to be the reference point for my energy 0. That's how Newton defined the kinetic energy. Okay. If we do that, then it means this constant should be minus m0 c squared. m0 is the rest mass. Okay. So if I define my energy this way, then when my particle is not moving, when my object is not moving, my mass equals to m0 and the energy is 0. Okay. So this convention has the advantage. When the energy is 0, I know my particle is not moving. Okay, so this is actually the definition of kinetic energy. That's we are following the same convention as Newton. So this convention is nice, okay, because it tells us if the particle stopped moving, the energy goes to 0. That's a very natural reference point for energy. However, there is one question. Okay, so the question is, in Newton's assumption, in Newton's convention, the reason he chose velocity 0 to be the reference state, let's say the rest mass c squared to be the reference state, is because Newton knows in Newton's mechanics, if the particle stopped moving, its energy cannot be lowered any further. A stationary object already reached the lowest possible energy. Okay, so that's why Newton chose this lowest energy state as his reference, so the energy is always positive. Everything is very nice. Okay. But in special relativity, that's not obvious at all. Okay? In special relativity, it is not obvious whether if a particle, if an object stopped moving, and then it reached the lowest energy state or not. Okay? Whether this is the lowest energy state or not in special relativity cannot be answered by the fundamental principles we studied earlier. Okay? So in early on of this semester, we studied several fundamental principles. For example, the principle of locality, the principle of special relativity, different reference frames should have the same physics law. So equation need to take this scalar equals scalar, vector equals vector structure. Okay, we have those. And we also have the fundamental principles that like the physics should recover Newton's law when the particle is moving slowly. Okay, so we have a bunch of physics law. None of those physics law tells us whether when a particle stops, when an object stopped moving, when the velocity becomes 0, whether that is the lowest possible state this system can stay or not, whether the system can further lower its energy or not. None of them answer this question. Okay, so that is something else. It's something beyond those fundamental principles. We need to look at experiments and look at our, so this is not something math can tell us. We need to look at our universe and the experiments in our universe and ask the question, what does the experiment say? Does the experiment say, oh yes, indeed, or if the particle stops moving, the energy cannot be further lowered? Or the experiment tells us, even if a particle stopped moving, even if an object stopped moving, there is still a way to reduce its energy. Okay, so that can only be answered by experiments, and we need to ask the experimentalist to check, in other universe, whether we have the first scenario or the second scenario. Both these two scenarios are compatible with the fundamental principles we discussed earlier. Fundamental principle we discussed earlier does not tell us which one is true, but they don't exclude neither of this either. Okay, so we don't know from fundamental side. And experimentally, in the early part of the previous century, people discovered that indeed the energy of a system can be further reduced, even if it stopped. Okay, that is from radiation. Okay, in the about 100 years ago, people noticed that particles can have decay. Okay, and when this particle is decay, and after the particle decay procedure, the mass of the system is actually reducing. Okay, so in that sense, the stationary object is not the lowest energy state. We can still have energy even lower. Okay, or I'll say the mass can be still even lower, even if the particle is stationary. Okay, so for example, nowadays we understand this very well. Okay, even if, so suppose we have, say, one positron and one electron. Okay, and we put them together, we put them close to each other. The total mass is roughly speaking twice the electron mass, because positron and electron have the same mass. Okay, and this bond state between positron and electron, we can form a bond state like hydrogen atom. This object, even if it stopped moving, I can still find a way to further reduce the mass. That is to let these two particles annihilate. After these two particles annihilate, they become a photon, and the photon don't have rest mass. Okay, so the bottom line, the rest mass of a system is not a fundamental physics constant. The rest mass of a system can change, and it can be further reduced down, even down to zero. Okay, so for example, when we annihilate a positron and the electron, the rest mass changes from twice the electron mass down to zero. Photon don't have rest mass. Okay, so experimental told us the rest mass of my system don't have a lower bound. My rest mass can go, even down to zero. In other words, the lowest possible energy state a system could have is actually zero. Okay, and because of that, we should use zero rest mass as my reference point for energy. And if I do that, that constant is actually zero. We can't put a constant there. And that actually gives me energy equals to mass c squared. Okay, so let me summarize. Okay, so our fundamental physics law only tell us energy and mass have this relation. Okay, but this relation does not tell us whether mass can be converted to energy or not, especially whether rest mass can be converted to energy and backwards or not. And that procedure actually depends on experiments. And if experiments tells us in our universe, rest mass can never be converted to energy. Rest mass is rest mass. It can never be further reduced. Then, it's just a mathematical relation. I can't say energy is the same as mass. Mass is the same as energy because it cannot be converted into each other. However, in our universe, we are very lucky. Okay, we could indeed convert rest mass into energy and energy into rest mass, like annihilation between a positron and the electron. Annihilation between positron and the electron, the rest mass changes from twice the electron mass down to zero. And those mass is gone, according to the E equals mc squared. When those mass is gone, it must be converted into energy. Okay, so the E equals mc squared is both a mathematical relation that comes from this principle we discussed earlier, and also a conclusion comes from experiments, where experiment tells us mass and energy can really convert into each other. And our fundamental principle and the mathematical duration tell us this relation, but this relation itself does not tell us whether mass can be converted to electron or not. That part was answered by experiments. Okay, and that was a separate principle and a separate principle of a separate fact of our universe. Okay, nevertheless, let's summarize. Okay, so in this section, we find that in order to follow this vector equals vector, scalar equals scalar structure, we have to modify our Newton's law. Okay, and after we modify the Newton's law to compare into this vector equals vector structure, we find that Newton's law pretty much survived, and the only modification we need to make is to remember the mass of particle or mass of object is not a constant anymore. It depends on velocity in this specific form. And the second consequence is that energy and mass times speed of light squared has a relation, has a very simple relation. Okay. And on top of that, experiment tells us mass can be converted to energy and energy can be converted to mass. So M and E is indeed the same thing. Okay. Mass and energy are the same thing. So in the future, when we consider energy conservation law, in addition to the kinetic energy, potential energy, all those energies, we also need to add the energy from the mass part, mass and speed of light squared. That is also part of the energy. And mass and energy can no longer be distinguished. Okay, so that is what we learned, what we discussed in this section. Okay, before we go to the next section, let's look at one more. Let's look at this 4D momentum one more time. Okay, so this is a 4D momentum we defined earlier. Okay, and this gamma m0 is mass in special relativity, as we just showed. Okay, and this object, okay, if we look at it more carefully, gamma m0 is mass, okay, and mass times Vx is my momentum x. Mass times Vy is my momentum y. Mass times Vz is my momentum z. Okay? So in other words, this 4D momentum, the last three components are my momentum in Newton's law, the same thing, px, py, pz. Except that the mass, I need to use the relativistic mass, which depends on velocity. Okay. And the first component is gamma m0 times speed of light. Gamma m0 times speed of light. Gamma m0 is actually mass, okay, relativistic mass. Speed of light, c, is actually c squared over c. I rewrite c and c squared over c. And mc squared, as Einstein told us, is energy. Okay, so the first component in my four-dimensional momentum vector, the first component is actually energy divided by speed of light. Okay, so this 4D vector is also known as the energy momentum 4D vector, because it contains both energy and momentum. Okay. In 3D space, energy is a scalar, momentum is a vector. You have two objects, one scalar and one vector. They are not related in Newton's theory. But in special relativity, this 3D scalar and 3D vector should be combined together as one 4D vector. That's my energy momentum vector. Okay. And this is a 4D vector. As we know, if we have a 4D vector, we can immediately define a scalar doing a unit product. Okay, so on this 4D momentum vector, unit product with itself. Okay, so unit product is defined as this vector times the metric tensor times the column vector as a column vector. Yeah. And this multiplication, if we calculate this matrix multiple product, we can easily show that this is energy squared divided by c squared, px squared minus py squared minus pz squared. Okay, that's straightforward from the multiplication. Okay, the px squared, py squared, pz squared. We know px, py, pz mass times velocity. Okay, so px, py, pz squared is actually m squared velocity squared, because p equals mv. This square is m squared v squared. So these last three terms combined together as mass v squared. And the first term, energy squared, energy is mc squared. So energy squared is m squared c to the fourth. Okay. If we massage the formula a little bit, we got mass squared times speed of light squared minus velocity squared. And the mass squared we know is gamma times m0. Mass is gamma times m0, gamma times rest mass. So I can rewrite this mass squared as gamma squared times rest mass squared. Okay. And then multiplied by c squared minus v squared. Okay. And one nice thing to notice here is gamma squared times c squared minus v squared is actually c squared. Gamma squared itself is this guy. So if we replace gamma squared with this guy, that's the definition of gamma, okay, we find that this unit product is actually m0 c squared. Okay. So the energy momentum vector unit product to itself is m0 c squared, rest mass c squared. Okay. And this guy is indeed a scalar. As we mentioned earlier on, rest mass is scalar, does not change from one reference frame to another. Speed of light is also scalar, does not change from one reference frame to another, invariant under Lorentz boost. So this whole thing is a scalar, does not change under Lorentz boost. Okay. So the inner product of the energy momentum vector to itself gives me a scalar. That scalar is rest mass square times speed of light square. Okay, it's a scalar. And yeah, this is this scalar. Okay, but notice that this same inner product can also be written in this way: energy square minus px square minus py square minus pz square. Okay, so the same inner product can be also be written in this way. And this px square, py, pz square added up together is just momentum square, total momentum square. Okay, so this inner product is E square over C square minus P square, but at the same time, it's rest mass square times C square. Okay, so it's the same inner product written in two different ways. So this must be equal to each other. Energy square over C square minus P square, that's this guy, must be equal to M0 square C square, that's this guy, because both of them comes from the same inner product. So they must be equal. Okay. From this formula, we can massage it a little bit, multiply C square on both sides and move P square to the other side. Now we get this. Okay. Energy of a system squared equals momentum squared times speed of light squared plus rest mass squared speed of light to the fourth. Okay. This is a very important relation. This is called the dispersion relation for relativistic particles. Okay. Dispersion relation tells me the relation between energy and the momentum. So for a relativistic particle, the relation between energy and momentum is this. Okay. So this is a very famous and very important relation. In relativistic physics, if we know the momentum of the object, and if we know the rest mass of the object, then we can use this to calculate the total energy of the system. Okay, so this is a very important relation. Okay, so that's a dispersion relation for relativistic particles. Okay, now let's switch to a new topic, and the section 3.3. So in this section, we'll explore the consequence of energy and momentum conservation law in special relativity. Okay, so I want to first emphasize that so far, when we discuss about special relativity in the previous sections and previous chapters, we have not yet proved energy and momentum conservation law should survive or not under special relativity. Okay, that's something we are going to do in the next chapter, chapter 4. Okay. So in this chapter, or in this section, let's assume energy and momentum conservation law still survives. Okay, we'll prove that in the next chapter, but here let's assume it still survives and ask what will be the consequence of energy and momentum conservation law. And we will demonstrate it using several examples. Okay. Okay. And the most important difference between energy and momentum conservation law in special relativity and in Newton lies in the fact, as we just mentioned, in special relativity, energy and mass can convert into each other. Okay, so we need to take that part into account. We can't just add kinetic energy and potential energy together and require this quantity to be conserved before and after some collision event or some decay. Okay, we have to take into account of the mass and the energy associated with the mass. That's mass times speed of light squared. Okay, so let's demonstrate this with a couple examples. So in the first example, let's consider a decay of a particle. Say we have one particle here, and more precisely, we are considering two-body decay. That's the simplest possible decay. Okay, so let's consider we have one particle. Okay, and this particle split into two smaller particles. A becomes B and C. Okay, so A is my initial particle, and then this particle split into two. Because it split into two, this is called a two-body decay. Okay, in reality, the decay of, like say, a nucleon or a quantum particle usually is more complicated. Usually, not always, but very frequently, if a particle decays, it will decay into multiple particles instead of the two. But for simplicity, let's focus on the situation, focus on the simplest situation. One particle decays into two smaller particles. A decays into B and C. And again, I want to emphasize here, we assume energy and momentum conservation law still works, and we will see what will be the consequence. Okay, so let's first look at what happens before the decay. Oh, so so in order to write down the energy and momentum and look at energy momentum conservation law, of course we will utilize our 4-dimensional energy momentum vector, energy and momentum. Okay, so let's first look at the energy and the momentum before the decay. Okay, so before the decay, I have one particle. This particle is A. Okay, and for simplicity, I will choose a convenient reference frame. Okay? The reference frame that I'm going to choose will be the reference frame where this A is not moving. Okay? So this A particle may be moving, doesn't matter. Even if it's moving, I can choose a reference frame that's moving with this particle so that it's not moving in that reference frame. Okay? And if the reference frame has a very convenient and very nice property, and that is because it's not moving, the velocity of A is 0 in this reference frame. Okay, when the velocity is 0, the momentum is at 0. The momentum is mass times velocity. Okay, so in this reference frame, it's very nice. The last 3 components of my energy momentum vector are just 0. And the first component is energy divided by speed of light. Energy is mc squared. And this m is ma. And ma stands for the rest mass of the particle A. Because in this reference frame, my particle A is not moving. I'm moving with the particle. Okay, so this reference frame, particle A is not moving. So the mass should just be the rest mass. So ma stands for the rest mass of particle A. Okay, so my energy, the first component of this vector is ma times speed of light, and the rest 3 components are just 0. Okay, so that's the energy and momentum vector before the decay. And the energy and the momentum vector after the decay will be like this. Okay, so here mb and mc again are the rest mass of particle B and particle C. It's not the mass, it's the rest mass. Okay, and for the momentum, the definition of the momentum is mass times velocity, x, y, z. Okay, mass and rest mass need a gamma to convert. This gamma b is the gamma for particle B, which is speed of light over square root c squared minus velocity of B squared. That's the gamma for B particle. Okay. For C particle, it's the same. Rest mass times gamma times velocity. That's the momentum. Okay. And the gamma for the C particle is the same formula, except this velocity should be the velocity of the C particle. Okay. So this is a momentum for the B particle. This is a momentum for the C particle. And for the energy, it's mass times speed of light squared. Okay, so the first component is energy over C, and this is energy over C for C particle. And again, for mass, it's rest mass times gamma, rest mass times gamma for C, rest mass times gamma for B, speed of light squared, speed of light squared. And we need to remember there is a 1 over C in the definition of the energy momentum tensor. That's this 1 over C. Okay, so this is the energy of B particle after the decay. This is the energy of the C particle, energy and momentum vector of the C particle after the decay. And the energy momentum conservation law here will mean this. Okay, the left-hand side is the energy and the momentum vector for particle A before the decay. The right-hand side is the energy and the momentum vector of B plus the energy and the momentum vector of the C. It's the total energy momentum after the decay, total energy and momentum before the decay, they should equal to each other. That's the energy and momentum conservation law. I want to highlight one fact here. Okay, this energy and momentum conservation law also satisfies this vector equals vector structure. On the left-hand side, I have a 4-dimensional energy momentum vector. On the right-hand side, I have a vector add another vector. Vector add a vector is still a vector. Okay, so I do have a 4D vector equals a 4D vector. This is very important because this means if in one reference frame I have energy and momentum conservation law, then I should have energy and momentum conservation law for all reference frames. Okay, so for any fundamental physics law, we should be able to write it in this structure. And for energy and momentum conservation law, we indeed could write it this way. Okay? Of course, this does not prove energy and momentum need to be conserved. But if energy and momentum conservation law is a fundamental law of our universe, it's better follow this structure. Okay, if it's follow this structure, then we know it's a fundamental law that stays the same in all reference frame. If it doesn't follow this structure, then what we will see is it's conserved in some reference frame, but not in others. That will be really, really weird. Okay. So bottom line is very nice. Everything is in this vector equals vector structure. Okay. So let's look into one component at a time. Okay, let's first look into the first component. The first component, this guy, should equal to the first component of the other side. Okay, the first component tells us this: MA equals MB times gamma B plus MC times gamma C. Okay, MA is the rest mass particle A, MB and MC are the rest masses of particle B and C. Okay, so this, the first component, is my energy conservation law, but at the same time, it is also the mass conservation law. The mass of my initial state should equal the total mass of my final state. Okay, so energy conservation and the mass conservation are the same thing in special relativity because E equals mc squared. The last three components of this equation gives me my momentum conservation law. Okay, and the momentum conservation law here tells us two things immediately. First of all, the velocity of particle B and C must be in the opposite direction. Okay, because momentum of, this should be PB plus PC. Momentum of particle B plus momentum of particle C should equal 0. Okay, so the only way to make sure that the two vectors can add up to 0 is to make sure these two vectors are pointing exactly on the opposite direction. If there is an angle between these two vectors, if they're not pointing opposite to each other in the opposite direction, if there is an angle, then when we add them together, it can now be 0. Okay? If we want the total momentum to be 0, we need to make sure that the velocity of particle B and C are moving in opposite direction. Okay? So B and C are moving along the same line, but in opposite directions. That's the first conclusion. And secondly, in order to make sure that they perfectly cancel each other, the total momentum of particle B and total momentum of particle C need to equal to each other. Okay, so this is the amplitude of velocity for particle B. This is the amplitude of velocity for particle C. They should equal to each other. In other words, these two momentum are pointing along different directions, opposite directions, and they have the same amplitude. That's the only way to make total momentum equal 0. Okay, and combining this energy and momentum conservation law together, we got two equations. The first equation is the mass conservation law, and the second equation is the total momentum of particle B. The momentum of particle B and the momentum of particle C need to have the same amplitude. Okay. On top of that, we also have the one additional condition. That condition is VB and VC need to point into anti-align, pointing in the opposite direction, and that is actually what is required from energy and momentum conservation law. And we can rewrite these two equations explicitly. We can rewrite this gamma B and gamma C out. Okay, gamma B is C over square root of this guy. Gamma C is C over square root of this guy. Okay, it contains velocity of particle B and the velocity of particle C. Okay, and for that's mass conservation law, energy conservation law. For the momentum conservation law, it's the same thing. Okay, we can write down gamma and C over square root. That's the definition of gamma. Gamma C is speed of light over this square root. Okay, so it's the same equation, just we written out explicitly what are those gammas. We have two equations, okay, and we have two unknowns, VB and VC, velocity of my B particle and the velocity of my C particle. And the nice thing here is we have the same number of equations and same number of unknowns, which means I can find a unique solution for this problem. Okay. That is, I want to emphasize, that is a special property of two-body decay. For two-body decay, one particle decays into two particles. The number of equations and the number of unknowns precisely equal to each other. So we have a unique solution. But if we consider more complicated, say three-body, four-body decay, this is not generically true. So this is only true for two-body decay. Nevertheless, if we have a two-body decay, the velocity of particle B and the velocity of particle C can be solved by solving these two equations. I will not bother you with the detail, but you can verify this is the solution of these two equations afterwards. Okay, and this solution is very nice. This solution of velocity of particle B and the velocity of particle C only depends on speed of light, C, and also the rest mass of my particles. Okay, as long as I know, say, this particle decays into this particle and this particle, A decays into B and C, as long as I know what type of particles I have, as long as I know the rest mass of those types of particles, I can get MA, MB, and MC, and I can get a unique value for VB and a unique value for VC. Okay, so this decay, by just requiring energy and momentum conservation law, I already know what's the final velocity of my particle B and C would have after this decay. That is actually a very nice property. Okay, and from this velocity, we can derive several very useful formulas. So for example, once we know the velocity of B and the velocity of C, we can immediately calculate the momentum of particle B. Sorry, this is another typo. It should be PB and PC. The momentum of particle B and the momentum of particle C. Okay, the momentum of particle B and the momentum of particle C is this guy. Okay, we know momentum of particle B and momentum of particle C should be equal to each other. That's the only way to make sure the total momentum is 0. Okay, so they should have the same amplitude. The momentum should be equal to each other. This is momentum for particle B. This is momentum for particle C. VB and VC, we now have the value for VB and VC. We just need to plug in the value of VB here, okay, or plug in the value of VC in this side. Then we'll get the total momentum particle B and C. Sorry, this will be PB equals to PC equals this guy. Okay, so after this decay, the momentum of the two particles, the amplitude of the momentum, we know it. It only depends on the rest mass and speed of light. Okay, and we also can get from this solution that VB and VC must be smaller than speed of light. Okay, and this is quite straightforward. If you look at the VB and the VC, okay, you have speed of light multiplied by a factor. This factor is 1 minus something. 1 minus something must be smaller than 1. Okay, so this is speed of light multiplied a factor smaller than 1, which means VB must be smaller than speed of light, and VC must be smaller than speed of light. This is a very important self-consistency check, because as we learned in previous weeks, speed of light cannot go beyond, speed of an object cannot go beyond speed of light. If we go beyond speed of light, we were having trouble with causality. The cause and the result would flip. Okay, so we will cause trouble. So in order to maintain causality, particles cannot travel faster than the speed of light. And the energy and conservation law tells us, indeed, no matter what we do, no matter what particles we use, what MA, MB, MC we choose, the final decay must have velocity smaller than speed of light. Okay, so that's the second thing we can learn from this. And another object, another condition, another conclusion we can learn from this calculation is that the mass of my particle A must be larger than the mass of particle B and C. Okay, this comes from the energy conservation. If you look at the energy conservation or the mass conservation, so this is this equation here. The initial state of mass is rest mass of A. The final state of mass is MB times gamma B plus MC times gamma C. Okay. Remember, gamma is a factor that's larger or equal to 1. Okay. When the velocity is 0, gamma is 1. When the velocity is not 0, gamma is always larger than 1. Because gamma is larger than 1, this M gamma plus M gamma must be larger or equal to MB plus MC. Okay. This means the mass of my particle A cannot be smaller than the rest mass of my final particles. In other words, quantum decay or decay of particle can only happen from heavier particle decays into lighter particles. We can't start from a lighter particle and decay into heavier particle. That cannot happen. Mass can only reduce, can only goes down when we do the particle decay. Okay, that is something that's necessarily have to be followed. Okay, so that's another very important conclusion. Okay, so this last conclusion, mass can only go down. The rest mass of the particle can only go down when we go through the decay. This conclusion can be generalized to any number of particle decay. So 3 particle decay, 3 body decay, 4 particle decay, n body decay. It must always satisfy this relation. So if we start from one particle, say particle A, and decays into a bunch of particles, say B, C, D, E, F, then the rest mass of particle A must be larger than the rest mass of all other particles it decays into. added together. Okay, so this is very important. It's a very important constraint. And this constraint also have direct implications in experiments, in particle physics. For example, we know that neutron can decay into a proton and electron, and at the same time, it will give out a neutrino. Okay, neutrino mass is very small. Electron mass is not very small, but much smaller than proton and neutron. Neutron and proton has very similar mass. Their mass is very close. But the neutron has mass slightly larger than proton. Okay, and it's larger than proton, so that it's actually more precisely the mass of a neutron is larger than proton plus the mass of the electron plus the mass of neutrino. Okay, because neutron has a larger mass than proton, this decay from a neutron into a proton is allowed. That indeed happened in our universe. Okay, so in our universe, neutron has actually a quite short lifetime. If you have a free neutron there, it will quickly decay into a proton and electron and give out some neutrinos because the mass goes down in this decay. But the other way doesn't work. Proton never decays into a neutron and electron. Okay, so if we only look at the charge conservation law, proton has positive charge, neutron has zero charge, and I can, in principle, decay a proton into a neutron and a positron. Okay, that satisfies charge conservation law. But that decay never happened in our universe, and the reason is because proton has less rest mass than neutron, and decay from a lighter particle to a heavier particle can never happen. So neutron and the proton have very similar mass, but the neutron have slightly higher mass than proton. And the consequence, neutron is an unstable particle. It can decay into proton. But proton is a much more stable particle. It cannot decay to a neutron. Okay, so in our universe, if you measure the lifetime of proton, the lifetime of proton is beyond 1.6 times 10 to the 34 years. Okay, and remember the universe age of our universe is just 10 to the 10 years. So our proton, although we don't know exactly whether this is infinite long lifetime or not, the lifetime of proton is actually larger, much larger than the lifespan of our universe. Okay, so in that sense, proton is pretty much infinite long lifetime. Where for neutron has a very short lifetime. The lifetime is just 14 minutes. Okay, and this big difference is related with the fact these two particles have very similar mass, but one is slightly heavier. Neutron is slightly heavier. For the heavier particle, it can decay into the lighter particle, but the lighter particle cannot decay into the heavier particle. This is one reason why proton is so much more stable than neutron. Okay, so the lifetime differs by orders of magnitudes. Okay. Okay. So now let's continue. Let's conclude this section by one question. Okay. So I mentioned to you early on, when we have a particle decay, I can only have particle from heavier particle decays into lighter particles. Okay. But now let's and all these conclusions, all the discussions we had before assumed we are in a reference frame where my particle A is stationary, particle A is not moving. Okay, we did this when particle A is not moving. So how about we let particle A move? Okay, for example, if we let the particle A move at very high speed, then the mass of this particle A will increase. Okay, we know when a particle moves faster and faster, the mass becomes bigger and bigger. Say, for example, we get a proton. This proton itself, if it's not moving, it's lighter than neutron. But if we accelerate this proton, if we increase its speed to very close to the speed of light, then this proton, because of the gamma factor, this proton will have a huge mass. Okay, that mass can be much larger than neutron mass. Okay, if that mass is much larger than neutron mass, is that possible? We can decay that heavy proton into a neutron. Okay, if we just look at the energy conservation law, if the particle A is moving, we should also add the gamma A factor here. If we just look at the energy conservation law, from the energy conservation law itself, it says okay, because if the particle A is moving, we need to add a gamma A on this side. Then this side is ma gamma A. we only need MA gamma A to be larger than MB plus MC. Okay, and MA itself can be small, but MA gamma A, the moving mass, can be huge. So naively, by just looking at the energy conservation law or mass conservation law, naively we will say, oh, it seems okay if I let particle move, and this mass become heavier, the proton become heavier than neutron. So in principle, it should be able to decay into neutron. However, the true answer is no. Okay, even if we speed up the proton, the mass of this proton becomes very, very large, much larger than the neutron. It still cannot decay. Okay? And the reasons are twofold. First of all, it's because of the principle of special relativity. Principle of special relativity tells us the physics observed in one reference frame and the other reference frame must be the same. Okay, so the physics law, if we have it in one reference frame, it must be the same in the other reference frame. If in the reference frame we used before, the reference frame where the particle A is not moving, particle A cannot decay into B and C. Then in any other reference frame, this conclusion should survive because all different reference frames are equivalent to each other. Okay, all different reference frames should see the same physics law and the same conclusion. Okay, so that's the reason why we should not allow this proton to decay, even if we speed it up so that it has a very heavy mass. And the second reason it cannot decay is that this energy conservation law is only one of the physics laws. At the same time, we need to think about the momentum conservation law. Okay, it turns out if we speed up this proton to very high speed and very heavy mass, it's possible we can satisfy the energy conservation law by allowing it to decay into protons or into neutron and some other particles. But we cannot satisfy energy and the momentum conservation law at the same time. Okay, if we want the energy and the momentum law to be satisfied at the same time and solve the equations, again, we will find there is no solution. It's not allowed. Okay, this is actually not an accident. Okay, it's because as we can see here, energy and the momentum conservation law is described by a 4D vector, by the same equation 4D vector. In other words, energy and the momentum conservation law are no longer two separate physics laws. They are related. Okay? After a Lorentz boost, if we go from one reference frame to another, energy and the momentum mix together. Some momentum become energy and some energy become momentum. And energy and the momentum conservation law also mix. Okay? So in classical physics, we can talk about the energy conservation law, we can talk about momentum conservation law, but in special relativity, these are not two separate laws. These two laws need to be combined together as one four-dimensional vector physics law. Okay, so we can't just look at the energy conservation law separately. We need to consider energy and momentum conservation law together. When we have energy and momentum law, conservation law combined together, this proton to neutron decay, we can show that it cannot happen, even if we allow the proton to be accelerated and get a very large mass, much heavier than neutron. That's still not allowed. Okay, I think this is a good point to stop. So let me summarize. So today we derived the equation of motion based on the idea of vector equals vector, scalar equals scalar, etc. And we find that that leads to the E equals mc squared. And experiment tells us energy and mass can convert into each other. And then we utilize this energy and momentum conservation law to demonstrate if we have one particle decays into some other particles, we need to obey this rest mass relation. Okay, the rest mass of my initial particle can only be larger than the rest mass of the particle it decays into. Okay, so I think this is a good point to stop, and I will see you next time.